Jamie has 2.5 liters of mercury in a jar. What is the mass of this mercury if its density is 13.6 grams per milliliter? So we're going to use dimensional analysis here because the mole unit that we're discussing here in Unit 5 has everything to do with dimensional analysis. That's why we covered it in Unit 2, because it's really important to us. So in my problem, I have 2.5 liters of mercury in a jar, and I have the density of mercury at 13.6. So the 13.6 is going to be my conversion factor in this problem. So I'm going to start out with 2.5 liters, and I'm going to set up my table here. I'm given liters, though, and my density excuse me, is in milliliters. So I need to convert liters into milliliters first. So that's what I'm going to do. So on bottom, I'm going to say for every 1 liter, there is 1,000 milliliters. And then from there, I can go ahead and do my density calculation. So there are 13.6 grams per every milliliter. Okay. Grams per every 1 milliliter. Now, I put milliliters on bottom so that everything can cancel out. So liters cancels, milliliters cancel. I'm left in grams, which is a mass, and that's exactly what I wanted. And the answer that I'm going to get is going to be 34,000, and then that will be in grams. We are now beginning Unit 5, or Chapter 7 of our textbook, and this is going to be covering the mole. So we finally got here. Unit 1 was over sig fig, scientific notation. Unit 2 was dimensional analysis. Unit 3 was all about atomic structure. And then Unit 4, we just covered periodic trends in the periodic table. So now we're entering the mole, which is a great concept for chemists. And it's really important. We use the mole throughout the year. So this is kind of a foundational unit for us as chemistry students. So the more we pay attention and the better we learn this mole unit, the more successful that we're going to be in the next few units ahead. The mole is one of the 7 base units in the SI system. So far we've learned about meters, liters, grams. We even talk about seconds. These are all base units. And so now we're adding one. This is going to be new to us. This is called the mole, and it represents the amount of substance. Okay, the amount of substance. I like to say the amount of chemical substance, but the mole measures a quantity. We're going to learn this term called representative particles, and representative particles is the current form in which a substance exists. So we need to understand what representative particles can be so that we can start understanding what the mole is and how it quantifies things. So representative particles, kind of a vague term. It can mean atoms, ions, molecules, formula units, and then it says anything else. Personally, I don't care for that, but atoms, ions, molecules, and formula units. We learned about atoms in the last unit, or in Unit 3. We learned about ions in Unit 4. In this unit, we're going to learn the difference between molecules and formula units. Okay, but all of these things are what we call representative particles. Just as 1 dozen is 12 representative particles of eggs, so when we say 1 dozen, that would be 12 eggs. We could say a dozen of anything. If I have a dozen calculators, I have 12 calculators. If I have a dozen pencils, I have 12 pencils. A mole is just that. So a mole, it's not 12, that's a dozen, but a mole is this number right here. And we call it Avogadro's number. We're going to learn about that in a second. Okay, but a mole is 6.02 times 10, and that should be 10 to the 23rd. So 10 to the 23rd power. Representative particles. Now again, on the last slide, representative particles meant atoms, ions, molecules, formula units. So we're dealing with chemistry concepts here, but all the mole is just a way of representing a group of ions, molecules, or formula units. The reason that it's so large is because atoms and molecules are tiny. We can't see them. And so there are literally billions and trillions of atoms and molecules in every little substance that we look at with our eyes. So by using this number, we can quantify things in a way that's easy for us to understand. So I went ahead and wrote out what a mole actually looks like. So 6.02 times 10 to the 23, this number right here is what it actually looks like. And it's really, really large. And again, that's because we're trying to represent something that is incredibly tiny and we have a huge amount of. So if we're talking about specific atoms or elements, we can say that we have 1 mole of iron. And if we have 1 mole of iron, it means that we have 6.02 times 10 to the 23rd atoms of iron. If we have a mole of water, that means we have that many molecules of water. Same thing with table salt, NaCl. If we have that many formula units, then we have 6.02 times 10 to the 23rd of them. So if we have a dozen eggs, we have 12. If I have a mole of eggs, I have 6.02 times 10 to the 23rd eggs. You can have a mole of anything, but we really don't just say that we have a mole of something else. Usually it's used in chemistry for obvious reasons, because that's a huge number. We wouldn't actually go buy a mole of eggs. That would be really expensive. So to get an idea of exactly what a mole is and to grasp it a little bit with our brains, we saw the number on the other slide and it was really large, lots of zeros, but what does that actually look like if we were to visualize it with something that we could recognize? So if we had a mole of watermelon seeds, it would be able to fit inside of a melon that's about the size of the moon. If we have that many donut holes, we have a mole of donut holes, we'd be able to cover the earth, and it would be 5 miles deep. If we had a mole of pennies, we could stack it 7 times from Earth to the moon. If we had a mole of sand, it would be the amount of sand on the beach of Miami. And if we had a mole of blood cells, we would have more than the total number of blood cells found in every single human being on Earth. So the mole is a huge number. So before we move on, there's something that we need to learn. They're called diatomic elements. There are 7 of them. They need to be memorized because if they're not, when we are trying to do chemistry calculations involving moles, then we're going to be missing our calculations. We're going to mess up. So these diatomic elements are only stable if they're bound to each other. Okay? They're called diatomic because the prefix di means 2, and obviously atomic means atom, so 2 atoms. So these elements down here, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they all exist bound to themselves. So that's why you'll see N2, O2, F2, Cl2. The diatomic elements need to be memorized for this chapter, and there's 7 of them, and that'd be kind of tricky just to straight up memorize them, but we give you a memory trick in order to get that. So the first thing you can do is just memorize the simple phrase H. Broncliffe, which is kind of strange, but it's one way of learning it. H. Broncliffe, that gets all 7 of them in there. Or, my personal favorite, we would say 7th heaven. Now, why would we say that? Well, on the periodic table, the diatomic elements make the number 7 right here. And we say 7th heaven, and the heaven is representative of H because it starts with the letter H for hydrogen. So 7th heaven is another way that you could remember them. So again, these need to be memorized because when we do calculations and you include something like hydrogen or nitrogen or fluorine, we need to have that memorized so that when we do our calculations, we're not missing that extra atom that's bound together. The man who came up with this concept of a mole, his name was Amadeo Avogadro, and the mole, 6.02 times 10 to the 23rd, we call it Avogadro's number. And so he was the one who came up with this. So we need to be familiar with this scientist because he was the one who is responsible for this term that we call the mole. And you'll probably hear us phrase it this way, but a mole is a chemist's dozen, meaning it's just a way of counting. So really, overall, the mole is just a number. It's a way of quantifying really, really large numbers into something that we can easily recognize. So our newest conversion factor goes a little something like this. And what I recommend is that you guys put a little star. For me, I'm putting this puffy cloud of greatness over it because we're going to use this conversion factor a lot. It says we work these problems using dimensional analysis. So if you were having problems with dimensional analysis in the last unit, you need to go back to our website, check out the dimensional analysis videos, and get yourself caught up on the t-table, okay, and canceling out units. That's going to be huge. So right away, if you know that you're not very strong on this t-table concept and canceling units, you need to go back and you need to basically refresh or come in for tutorials and we will reteach the information to you. So here's our first mole problem, and it goes something like this. How many moles are there in 1.2 times 10 to the 25th, and that should be raised to the power, atoms of phosphorus? Okay, so it's going to go a little something like this, so follow along. I'm going to start out 1.20 times 10 to the 25th power, and then this is going to be atoms. Now, I recommend strongly that you label. You don't just write the number, you write atoms, okay, of phosphorus. You need to recognize somehow, because when we start getting into chemical reactions, you're going to have to know exactly which chemical or which element or which molecule you're going to be dealing with so that you know. So I'm going to put atoms of phosphorus because that's what my question gave me. Now, on the bottom, okay, we are going to use the mole because the mole can be used as a representative particle. So, in this case, I'm going to say that in every 1 mole, I'm going to put moles on the top because that's what I'm going into, in every 1 mole of phosphorus, okay, I have 6.02 times 10 to the 23rd atoms of phosphorus. And again, that's why I put it on bottom, because it needs to cancel. So I'm going to go ahead and calculate this out, and I'm going to get an answer. I'm going to get an answer of 19.9335. Okay, and I'm getting a bunch of digits here. So let's talk sig figs. In this answer, or in this problem, I was only given one number, and for us, it's a measurement. Now, we didn't measure it ourselves, but we take significant digits based upon measurements. And so with this measurement, I have 3 sig figs here. There's a trailing 0, which is significant if there's a decimal point. So in my answer, I need 1, 2, 3 sig figs. That 3 will not round that 9, so my final answer is 19.9, and then I'm going to label it as moles of phosphorus. Okay, and there's my answer. In the next problem, I am doing just the opposite. How many atoms are there in 0.75 moles of zinc? So I'm going to start with 0.750 moles of zinc. Moles of zinc. Alright, so for every 1 mole of zinc, and again, this can be any element. It can be moles of zinc, moles of hydrogen, moles of water. In this problem specifically, it's zinc. For every 1 mole of zinc, we have Avogadro's number, 6.02 times 10 to the 23rd atoms of zinc. So units will cancel, Moles of zinc cancels top and bottom, and the answer that I get is with sig figs, I have 3, 4.52. 4.52 times 10 to the 23rd, and that is going to be atoms of zinc. We're going to keep going and do another example. How many molecules are in 0.4 moles of N2O5? Now, what's different about this one, we are not using atoms now, we're using molecules. And again, that's a representative particle. Atoms, ions, molecules, formula units, all of those are representative. So we can use moles to represent them. So in this case, we're just using molecules. Nothing changes about our process. It's all the same. Okay, so I'm going to start out by drawing my table. How many molecules are in, and I am using 0.4 moles of N2O5. And like I said, make sure that you're writing this down. Okay, moles of what? N2O5. Be specific. The more specific you can be, the better off you're going to be in this unit. Okay, and we're trying to go into molecules. So, for every 1 mole of N2O5, I'm going to have 6.02. Excuse me, let me try that again. 6.02 times 10 to the 23rd molecules. So a mole can be all the representative particles. So in this case, again, molecules of N2O5. Moles cancels on the bottom. Now, you'll note that my spelling is different here than it is here. We can use either spelling. It's okay as long as we know that they're both moles. Okay, that's up to you. After this, my answer will be with correct sig figs, which is 3. I have 1, 2, 3 here in this number. The leading 0 is not significant. 2.41 times 10 to the 23rd, and that's going to be molecules of N2O5, dinitrogen pentoxide. How many moles are contained in 1.20 times 10 to the 24th molecules of CO2? So here we go. I'm going to draw my table. How many moles are in 1.2 times 10 to the 24 molecules? Now I'm going to abbreviate here of CO2, but make sure that I make sure that I know that MOL in this case is molecules. So whatever you label, just make sure that you know exactly what you're talking about. In 6.02 times 10 to the 23rd molecules of CO2, I'm going to have 1 mole of CO2. Molecules will cancel. Molecules cancels here and here. I'm left with moles of CO2, which is what I wanted. So I'm going to go ahead and draw my finish line over here, and then I'm going to calculate. And my answer will be, with 3 sig figs, 1.99 moles of CO2. And that is my answer. The next important concept is called gram atomic mass. We might call it formula mass, we might call it molar mass, we might call it molecular weight. There's all kinds of things that we can call it. Here we're going to call it gram atomic mass. And what that is, it's the atomic mass of an element, but we put it into grams, something that we can recognize, rather than atomic mass units, which is a lot different. This mass, which is here on the periodic table, comes from the mass of just 1 mole of atoms in a monatomic element. So for instance, if we had 1 mole of phosphorus right here, which is 6.02 times 10 to the 23rd atoms, if we had all of those atoms in a little bowl and we weighed it on a scale, it would weigh 30.97 grams. Okay, so we're going to use these numbers on the periodic table often, and we're going to use it to find the weight in grams of an element or a compound. When we're going to use the measurements up to 0.01 grams. Okay, so for instance, in phosphorus here, it's 30.97. What we're going to do is go to the nearest 0.1, which means we would use the 7 to round the 9. In this case, it would bump 30 up to 31. So we would put 31.0 in this case, and that's what we would use for the molecular weight. So to help understand this concept a little more clearly, let's think of carbon. Okay, carbon is an element that was kind of used to first base this idea of molar weight or molecular weight or an atomic mass. If we have 6.02 times 10 to the 23rd atoms, we're going to have precisely 12 grams of carbon. Okay, and the reason that carbon is just 12.0 grams and it's not something like 12.2 or 12.4 is because carbon was used, again, as the basis for this idea of atomic weight. Carbon's a pretty important element, but it was so important that they went ahead and used it in order to figure out this concept of atomic mass. So, for the sake of our measurements, what we're going to be saying is that molar mass, or this idea of mass for an element, is going to be used as a conversion factor. We're going to say that there are 12 grams in every 1 mole, or 12 grams per mole. And that would be the atomic mass of carbon, or the molar weight. And so I've hinted at this before. You're going to have to get used to the idea of hearing different terms that we use for this. So we've called it gram atomic mass. We might be calling it gram molecular mass. We might be calling it gram formula mass, depending on what type of compound we have. We can call it molar mass. This is personally the one that I use the most. I like to call it molar mass. We can call it molecular weight. There's all kinds of different things, okay, but they all mean the same thing. So we have to get familiar with calling it different things. So this is going to be gram molecular mass, and what molecular mass means is if we have a molecule. So a molecule, which we will learn about in a couple of units from now, a molecule means that you have 2 atoms that are covalently bound. But for now, we're just going to call it gram molecular mass. So if I have 1 mole of H2O, what I'll do is go ahead and add up the weight for each one of the atoms. So I will have exactly 2 hydrogen atoms and 1 oxygen. So if we look at the periodic table, hydrogen has a weight of 1.0 grams, and that's for every mole. Here I have 2 hydrogen atoms, so I'm going to have to multiply that value from the periodic table by 2. And so what I'll get here is 2.0 grams. Now let's do the same thing for oxygen. If I look at the periodic table and round to the nearest 0.1, I will have 16.0 grams for oxygen. And I will multiply that by 1 because I only have 1 oxygen. So, total, I will have 16.0 grams of oxygen. Now, to find the gram molecular mass, or what I call molar mass, we just simply add up those values. And in this case, we're going to get a molar mass of 18.0 grams. and that would be the weight of water if I had 1 mole. So this will be grams per mole of water. Let's do one more example. What is the gram molecular mass, or what we call the molar mass or molecular weight for CH3OH? So another way of working it out is I'll go ahead and come over here and I'll write out the elements that I have. I have carbon, I have hydrogen, and I have oxygen. And what I'll do is I'll go ahead and find the atomic weights for each one. So on the periodic table, I'll go and find carbon, and carbon has a mass of 12.0 if I round to the nearest 0.1. Hydrogen, which we saw on the last one, is 1.0, and oxygen is 16.0. So what I'll do is I'll count up the atoms for carbon. In this case, it's just 1. And let me change the color of my pen. So I will multiply this weight for carbon by the number of atoms, which is just 1. Hydrogen, it's H3, but then there's another H on the OH, so total there are 4 hydrogen. And for oxygen, I have just 1. So I'm going to go ahead and take those values, multiply them out. I will get 12.0 for carbon. I will get 4.0 for hydrogen, and I will get 16.0 for oxygen. So I'm going to go ahead and add all of those values together, and I will get 32.0 grams. And again, this is grams for every 1 mole. So all of these values are coming from if I had just 1 mole, which is 6.02 times 10 to the 23rd molecules of this compound. So it's going to be grams per mole. So the next term is gram formula mass, and it's the exact same thing as gram molecular mass. The only thing that changes is the name. That's literally it. This will be, and again, we haven't learned this yet, this is going to be when we have ionic compounds. Gram molecular mass was based on covalent compounds. Gram formula mass is going to be based on ionic compounds. The process is the exact same. You're just adding up the atomic masses in a formula unit, which is a ionic compound. So we're going to find the GFM, or the gram formula mass, or the molar mass, or the molecular weight of magnesium phosphate. Well, what is magnesium phosphate? I will tell you. It is Mg, that's magnesium, Mg3, and then phosphate is something called a polyatomic ion, which we'll talk about in probably the next unit or the next one after that. Phosphate is PO4, and that is going to have a 2 on the outside of it. So this is going to be just a tad bit different, but the process is the same. So I'm going to go ahead and write out the elements that I have. I have magnesium, I have phosphorus, I have oxygen, and that's it. Now, the next thing I'm going to do is find the masses. The mass of magnesium is 24.3 grams if I look at the periodic table. The mass for phosphorus is 31.0, and the mass for oxygen, which we have seen, is 16.0. Now I got to find out how many. I had 3 magnesium, so I multiply it by 3. Phosphorus. Now, there is 1 phosphorus here. When I have a 2 on the outside, like this, okay, what happens is it distributes. It distributes throughout whatever is inside the parentheses. Not the whole thing, not the magnesium, just what's in parentheses. So this 2 is going to distribute to both the phosphorus and the oxygen. Okay, it's kind of like algebra. So I'm going to have 2 phosphorus atoms here. And then what about oxygen? Well, the 2 is going to distribute over here. So we don't add this. It's not going to be 2 plus 4 to get 6. It's going to be 2 times 4 to give us 8. So if you need to star that or make a note of that yourself, go ahead and do that. We do 2 times 4 there. When I multiply all these out, I'm going to get 72.9 for magnesium. I'm going to get 62 for phosphorus, and I'm going to get 128 for oxygen. And when I add all of them together, I am going to get 262.9 grams per mole of Mg3PO4. So that's my final answer. And our last example for the day is going to be finding the molar mass of ammonium sulfate. Ammonium sulfate. So what is the compound ammonium sulfate? It goes something like this. In parentheses, NH4, that is ammonium. And it's going to have a 2 here. Sulfate is SO4, just like that. So there's the compound ammonium sulfate. We're going to find the molar mass. I have nitrogen, I have hydrogen, oxygen, and sulfur. So I got 4 compounds here. Let's find the weight. The weight of nitrogen is going to be 14.0. The weight for hydrogen, 1.0. Oxygen, 16.0. Oops, that is not 0. And then sulfur is going to be 32.1. And these are all grams here. Now I got to count up how many there are. The 2 distributes to the nitrogen, so there are 2 of them. The 2 distributes to the hydrogen. 2 times 4 is going to be 8. We don't add them up. Oxygen. I have 4 of them over there. And then the sulfur is just 1. Okay? Keep in mind, let's make a note here, that this 4 does not distribute to the sulfur. Okay, we don't do that. The 4 is on the oxygen. The only reason we would distribute is if the 4 was in parentheses outside. So let's add them up. We get 28.0. For nitrogen, we get 8 for oxygen. This is going to be 64 for oxygen. And we are going to get 32.1 for sulfur. We get a value of 132.1 grams per mole of ammonium sulfate.